Ever wondered how quantum physics and the universe share a symbiotic relationship? It's a fascinating connection, one that's best understood through the lens of the non-commutative quantum tensor network. Let's begin by dissecting the quantum tensor network. Picture it as a web of nodes, each associated with a Hilbert space, which is essentially a complex inner product space. These nodes are interlinked by a non-commutative algebra of operators. The total Hilbert space of the network is the tensor product of the individual node spaces, and the quantum state is depicted by a density matrix. The dynamics of this network are formulated using a path integral approach. This involves an action functional made up of a quantum information theoretic term and a gravitational term. The path integral measure is constructed using the Haar measures on the local unitary groups acting on each node. This network also incorporates the holographic principle. This principle relates the bulk and boundary tensor networks through a holographic mapping. The entanglement entropy of boundary regions is related to the area of minimal surfaces in the bulk, as described by the Ryu-Takayanagi formula. The framework interprets the holographic correspondence in terms of quantum error correction. Here, the bulk degrees of freedom act as logical qubits and the boundary degrees of freedom as physical qubits. This offers a robust method to store and process quantum information in the presence of errors and noise. The framework uses tensor network renormalization techniques to study the scale-dependent properties of the quantum tensor network. This renormalization flow in the boundary tensor network induces a corresponding flow in the bulk, which is interpreted as the emergence of the holographic spacetime. The dynamics of the emergent spacetime geometry are derived from the variational principle applied to the gravitational action term. In the classical limit, this yields the Einstein field equations, while quantum corrections lead to deviations from classical gravity at short distances and high energies. The framework explores the connections between quantum information and thermodynamics, interpreting entanglement entropy as a measure of thermal entropy in the context of holography. The irreversible evolution of entanglement in the quantum tensor network is seen as the origin of the thermodynamic arrow of time. Lastly, this model predicts various quantum gravity effects that could be tested experimentally. These include modifications to the gravitational wave spectrum, deviations from classical general relativity, and signatures of spacetime non-locality and entanglement. It also provides a platform for quantum information processing and computation, with potential applications in quantum simulation, machine learning, and cryptography. In conclusion, the non-commutative quantum tensor network is a robust and fascinating model. It bridges the gap between quantum physics and the universe, shedding light on the intricate dynamics that govern them. While it's a complex concept, it's one that holds the potential to revolutionize our understanding of the universe and its workings.